Hello everyone, I'm Shantisri and I'm excited to present a project on predicting patient outcomes in the ICU. Our work focuses on using artificial intelligence to assess doctors by making better and earlier predictions of mortality and length of ICU stay. This can ultimately support clinical decisions, improve ICU resource management, and even save lives. The base paper that we are building on proposes a hybrid LSTM graph neural network model for ICU predictions. Here's the main idea. LSTMs are very effective in handling temporal data such as patient vitals recorded continuously in the ICU. But outcomes don't depend only on vitals. Patients who share similar diagnoses may also have similar risks and patterns. To capture this, the paper uses a graph neural network. The GNN builds a patient graph where nodes are patients and edges represent shared diagnoses. By combining the LSTM's time series learning with the GNN's relational learning, the model can predict outcomes such as in-hospital mortality and length of stay more accurately than using just LSTMs. Our project extends this approach using the Cynthia dataset. Coming to the problem definition, predicting ICU outcomes is challenging because existing models mostly rely on time series vitals like heart rate, blood pressure, oxygen levels, etc. However, they often ignore sparse but important information like diagnosis, including rare conditions. This leads to less accurate predictions and limits how useful these models can be in real world ICU settings. The problem we are addressing is how can we combine time series vitals with diagnosis information to build a more accurate model for ICU outcome prediction. For this milestone, our in-scope work is using the Cynthia dataset, which includes static features like age and gender, time series vitals, and diagnosis, constructing patient graphs using diagnosis, training an LSTM GNN hybrid model, and comparing it against baseline LSTM models. What is outscope includes real-time deployment in hospitals, integration with medical devices, and using datasets beyond eICU. Our focus is only on model design and training at this stage. In this work, we propose a pipeline that combines LSTM and graph neural networks. The LSTM captures the temporal patterns in early clinical time series, while the GNN models interpatient relationships through patient similarity graphs. We also include static and sparse features like diagnosis to enrich the representation. The joint model is trained for predicting in-hospital mortality and length of stay, and its performance is evaluated using metrics like AUROC, AUPRC, MSC, etc., along with ablation studies to check component contributions. The expected outcome is more accurate and interpretable predictions than traditional models, which can help doctors prioritize care and optimize hospital resource planning. Our system architecture is divided into five main layers: front-end, back-end, AI model, database, and cloud deployment. Starting with the front-end, we use a React application where users can log in, view dashboards, and upload patient data in tabular form. These requests are sent as API calls to the backend, built with Fast API, which handles request routing, model integration, and communication between the front-end and the AI model. The AI model consists of two parts: data preprocessing and the deep learning pipeline. Patient time series data is processed, passed through an LSTM encoder to capture temporal patterns, and then into a graph neural network, which is GNN layer, which models relationships across patients. The model outputs predictions like in-hospital mortality or length of stay along with recommendations. All outputs are stored in the database layer implemented in MongoDB. This database keeps raw patient data, uploaded files, and generated predictions or reports which can later be retrieved by the front end for visualization. Finally, the system is deployed in the cloud with separate hosting for the front end, back end, and model. A CI/CD pipeline ensures smooth updates while the database and model are also hosted for scalability. In short, the architecture connects user interaction at the front end to advanced AI predictions at the back end with robust storage and cloud deployment ensuring accessibility and efficiency. To conclude, our work shows that combining LSTM with graph based learning provides a powerful way to model ICU patient data. LSTM effectively captures the temporal patterns present in clinical time series, while graph learning adds the ability to model relationships across patients, something traditional models often fail to do. Together, this hybrid approach achieves higher accuracy in predicting both in-hospital mortality and length of stay, which are two of the most critical outcomes for ICU management. What makes this especially important is the impact on real-world healthcare. Accurate early predictions can guide doctors in taking timely interventions, allocating resources more efficiently, and planning treatment strategies with greater confidence. Moreover, by moving beyond traditional machine learning, this approach offers a more data driven and interpretable framework that can adapt to complex hospital environments. In short, this study demonstrates that advanced AI techniques like LSTM combined with GNN not only outperform older baselines but also have the potential to support better clinical decisions and improve overall hospital resource management. Thank you.